Good evening, Amit sir.
Good evening, ma'am. Good evening.
Yeah, sir. We'll wait for another 5 minutes.
No issue, ma'am. Is my
Yeah,
voice audible?
yeah, sir. Yeah.
Okay.
ജോഷുവ സ്ട്രെങ്ത് കൂട്ടാൻ എന്തെങ്കിലും പോസിബിൾ ഉണ്ടോ നോക്ക്.
Yeah, Amit sir.
Yes, ma'am.
Yeah, can we start?
Yes, yes.
Yes. So, good evening, everyone. I take this opportunity to express my sincere gratitude to Dr. Amit Kamra, Professor, whose invaluable guidance and constant support played a pivotal role in enabling us to using the ATAL FDP. His mentorship was instrumental at every stage, from structuring each component to guiding us throughout the entire process. This achievement would not have been possible without his continuous encouragement and unwavering support. The first day and the inaugural session of the program will begin with Dr. Amit Kamra setting a strong and insightful foundation for the FDP through his expertise and leadership. So, good evening, everyone. May I request you all to please turn on your cameras briefly for a group picture. I repeat, may I request you all to please turn on your cameras briefly for a group picture.
Hello, King sir. Is my voice audible?
Yes,
My
sir, it is audible.
okay.
Yes, yeah. Yes, now I hand over it to Miss Sumi.
Simi, your voice is not audible, I think.
Simi, please turn on your mic. Not audible. Simi?
There is some noise at her end, I think.
Yeah, sir.
Tell her to join, exit, and join back again.
Simi, is it audible to you? Can you hear us? Yeah.
But she's not audible, I think. Uh,
Simi?
Hello.
Yeah,
yes.
yeah.
Yes, you're audible, ma'am.
Okay, thank you, sir. Okay, good evening, everyone. It's my great honor to extend a warm welcome to our distinguished resource person, Dr. Amit Kamra, Associate Professor in the Department of Information Technology at Guru Nanak Dev Engineering College, Ludhiana, an autonomous government aided institute of repute. Dr. Kamra has an illustrious academic career spanning over 24 years of teaching experience and significant contributions in the field of computer science, artificial intelligence, cybersecurity, machine learning, NEP 2020, digital forensic, and numerous emerging domains. He has been honored with the coveted Best Teacher of North India award by IST twice, first in December 2021 and again in November 2024, a recognition of his excellence in teaching, mentorship, and academic leadership. Dr. Kamra is a prolific researcher having guided 34 MTech dissertation and 5 PhD scholars so far. He has secured research and academic grants exceeding 42 lakh from prestigious agencies including AICTE, ATAL, UGC, SERP, and PTU Jalandhar. It is also noteworthy that Dr. Amit Kamra has received three ATL grants in a row, demonstrating his sustained expertise and credibility in the academic research ecosystem. He has delivered more than 160 expert talks across India at many reputed institutes, universities, and central level organizations, including IITs, universities of national recognition, AICTE approved FDP platforms, and various technical institutions, including those in South India. His academic qualification include a PhD in computer science from SLIET, Longopal, and MTech with honors from Punjabi University, Patiala, and a BTech from PTU Jalandhar. Apart from academics, Dr. Kamra has also been deeply involved in language empowerment initiatives, having been selected by IIT Madras, IIT Kanpur, and AICTE New Delhi for the translation of Swayam NPTL content as part of the Sati project. He has already translated 5 engineering courses into Punjabi and 3 more are currently in progress. He is also presently working on an AICTE project for translating and converting the data structures and algorithm book into Punjab. With expertise cutting across multiple domains, including computer science, forensic, machine learning, cybersecurity, biomedical imaging, NEP 2020, and digital marketing, Dr. Kamra continues to contribute immensely to academia, research, and knowledge dissemination. We truly privileged to have him with us today as the part of faculty development program. We extend our heartfelt welcome to you, sir, and look forward to an insightful, enriching, and thought-provoking section under your guidance, sir. Thank you, and over to you, sir.
Thank you, Simi ma'am. It was a nice and very detailed introduction. Mostly generally the person who gives the introduction speak a few lines about me, but you read the whole achievements of mine, and I'm thankful to my very close friend Dr. Gan, Dr. King, and the co-coordinator and the other faculty members of Sahardya College who has given me the opportunity. Let me tell you brief about my college. My college is Guru Nanak Dev Engineering College. It is one of the oldest engineering college of North India. Let me share my PPT also. In between, we will keep on talking also. Anybody please confirm, is the PPT visible?
Yes, sir, it's visible.
Okay. Okay, my dear friend, I belong to one of the premier engineering college of North India. This college was established in 1956 by our late first president of India, Dr. Rajendra Prasad, in the year 1956, and from the last 21 years, I'm working here. Although I did my BTech in electronics, and later on I shifted to computer science with the change of time or with my interest. So I'm a field of two disciplines. I then did my undergraduation in electronics and later moved to computer science and IT for my PG and PhD. But anyhow, these fields are all interdisciplinary, and I hope all of you will enjoy this session with me today. Uh, In fact, I also have conducted ATAL program back to back three times in a row, and uh, last year the ATAL authorities has put some condition that the person who has got the ATAL grant will might not be able to get this grant again. So Dr. King, one fine day, he called me and he asked me, "Sir, uh, give me some idea of this topic." Dr. King is a common friend of my other friend in Kerala, and so I gave him this idea that, sir, try to apply on some theme related to semiconductors, because government of India is pushing a lot of effort in semiconductors, and and he made a very good proposal, and finally this FDP came to in existence. So this all happened around 4 to 5 months back, and with the efforts of Dr. King, who at least for the work for the 2 to 3 weeks in making that proposal, because out of 5,000 proposals, only 500 are being shortlisted, or maybe a number might be a bit more also. But still, to get a grant and to execute a grant is a very difficult task. And I must thankful to the authorities who have given me a session today. And in fact, this is the first session, and first session itself is a very responsible session, because in any FDP, the persons are not from all the domains. Some people might from the computer background, some people might be from the electronics, some people will be from the other areas of engineering. So it becomes a moral responsibility of some speaker to make a good ground of the complete FDP, which is going to be organized in this next 5 to 6 days. Your next speaker is a very versatile speaker. He is one of my very good friend. Please don't miss his lecture also, and he's very senior to me and working in the semiconductor area. I am working in machine learning AI, and now we are also starting thinking about how to incorporate semiconductors in machine learning. Uh, I'm very pleased to tell that Dr. King has given me two sessions because one of his expert has was not available. So he contacted me that, please, sir, can you accommodate one more session, because we cannot call any other expert. It has to be from the pool of the speakers which are already approved by AICT. So my today's session will be a theoretical coverage of the AI and machine learning, and bit of thinking things. We will talk about semiconductors also. While tomorrow session we will I will try to tell you something practically how machine learning is able to classify semiconductors. So we'll I have a practical session tomorrow. So today's session will be a ground, will be making the base of the whole FDP. And one more request to all of you, please be interactive with me. You can write the chat box also. You can unmute at any point of the time. I love to be disturbed. In fact, I want maximum interaction with all of you, because all of we are sitting at our comfort of our home. Even if you are driving or going or doing some other work, your ears are working. And this sort of FDPs are a source of decimation of knowledge to all of us. So, not wasting much time, let me tell you the theme of the today's session. I will discuss about current trends in AI and machine learning for VLSI physical design. You know, how this idea came into the mind. It was something, a term called Semicon India. Government of India in the year 2022 started thinking, it was a mission of the government of India that somehow some upcoming technologies should be involved in semiconductor design also. So I will be talking about Semicon India also, and these are the bit about the index of my today's session. I will talk a bit about Semicon India. We will discuss about machine learning, something which you have might not have studied in books also. We will discuss start of how AI started, how machine learning started, and how they together AI and ML they can be used in the semiconductor industry. Because our topic is something about the theme of the FDP is about AI. It is about IoT. It is about 5G. It is about semiconductors. There are four different areas which we have to touch, and some other speaker will be talking about 5G or IoT. So I will not be touching that uh, topics today due to the stipulated time given to me. So why the government of India is thinking about the semiconductors nowadays? From the last 2 3 years, government of India is pushing a lot of money in this area. In fact, I hope Dr. King got this FDP because it was one of the mission of the government that they want to create some reforms in the field of semiconductors. And since we all are academicians, we are the pushing force behind that research. So it happened in the November 2022 when a government of India published one report called Semicon India Future Skills Talent Committee report. I don't want to discuss that report. That report is a very big report. It is of 100 pages, but I want to tell you about the brief extract from that report. See, this roadmap for the semiconductors was created in the November 2022 by this that report, in which they provided some framework for the opportunities for scaling, reskilling, and upskilling in the field of semiconductors. And I am the person from basically from the computers background. The government of India want that the person from the interdisciplinary area should start working on this domain. Till now, semiconductor was a typical this VLSI, this integrated circuits was a typical electronics domain. But considering the research component available in the AI and the machine learning component, the government of India want to push all those things also in the area of semiconductors. So they started giving some recommendations, some certificate courses, and they were the minds were deliberating that some desired skill set in research, design, and fabrication can also be incorporated to develop the Indian semiconductor industry. Now, earlier Indian semiconductor was lot depending upon Taiwan, Japan, and this other countries, maybe China also. But from the last 2 3 years, there are a good number of companies who are developing this all products in the India itself. Dr. Jattana, your next speaker, he has worked in the semiconductor industry for the last 20 years, and I hope you people will be getting a very good stuff of information from him. Coming back to the Semicon report, that committee suggested that we need to develop all these things in our curriculum also. Because when I studied semiconductors in my BTech curriculum, there was nothing about AI or machine learning. So the committee suggested that there is a need to develop some framework for the collaboration of industry, academia, and the government to design these courses for some higher education system which can really boost the Indian semiconductor industry. Now, one of the important aspect which the government want is the usage of these advanced softwares, microcontroller programming, interfaces, and AI and machine learning. These components were not incorporated in our curriculum. Even till now, they are in the nascent stage. I will show you tomorrow that how machine learning will be able to do classification and do some sort of analysis, which I hope you people might not have seen till now, because the research is a new component. The research in ML and AI is rather a new term for all of us. Now, the demand for these different sectors in the semiconductors over the next 3, 5, and 10 years, we want some good results. So, based on the historical data, there are certain fields like design, it has a good growth of 10 to 15%. While over the last 15 years, we can see that year over year, the growth will be very large if we started incorporating AI and machine learning also in this industry. Now, till now, machine learning and AI has been very nascent to the field of the semiconductor industry. So, my presentation will be focused on these two domains only. Since this is an introductory lecture, first lecture, so while other speakers will be talking about these practical concepts also, so I will make the base of whole FDP in my session. If the time permit, I will tell you one small case study also that how we can integrate AI and machine learning for semiconductors application. While practically, I will show the whole concept in my lecture tomorrow. Tomorrow, I will discuss one tool. First, I will discuss that tool, and then later on, I will show the application of that tool in the semiconductor industry. Okay. So, my dear friends, let us move forward now. It is a small icebreaker for you. In between the lecture, I will keep on asking small questions so as to keep you ready with me, to keep you interactive with me. This is a one small question. How many sectors are broadly available for semiconductor industry? Can someone reply? or you can write the chat box also. You can Google it also if you want. I just want you people to be interactive with me. So I'm taking a 1 second break now. I'm stopping my presentation. I'm writing this question in the chat box. How many sectors are available in the semiconductor industry? I'm writing them in the chat box. It's a good if you can unmute yourself, or you can reply at your own by unmuting yourself. I'm stopping the presentation for a few seconds now. This is my question. Infinite Ravi Kumar Rayalaji. Ravi sir, Infinite, keep some value. I want some. How many sectors are broadly available for semiconductor industry? You can Google it. You can ask your chat GPT. You can use your brain. You can unmute also. Please attend the lecture for sake of knowledge decimation. Don't for the not for the sake of getting the certificate. Certificate Dr. King will give you. Don't worry. Realization using simulation testing. Thank you, Sangeeta ma'am. Design for testing, verification, validation. PD, okay, this DFT, DFDB fabrication. Very good answer. Ravi Kumar, Ravi sir, you have make it bit concise now because Infinite was a very big domain for me. Rajmi Rajesh, please give some number. Let us confine to some areas which we can tell our students also. If your student asks this question, how many sectors in his semiconductor industry can work? So give some, no, De Silva ma'am, I want the specific terms. Please be fast because this is a very new material test equipment, good one. 5 major sector. Yes, Randeep ma'am. Assembly packing is a very good answer. Assembling, packaging, anything else? Means which area we want the semiconductor industry is very dominant. Okay, thank you all of you. You have given a very good reply. My motive is to keep you attentive here. Please, I beg your pardon. It is not a viva voice, so please keep on answering your replies. It will make me a bit interactive, and I will be very happy if you. Yes, fabrication is also a area of concern here. I will be very happy if you unmute yourself any point of the time. You can ask me.
Yeah, basically it is the front end back end are here to
Okay.
GDS2 for front end and then the back end. So there are a lot of things that can be. Microelectronics actually is a huge branch.
Yes.
We call it
Abhay sir,
VLSI.
actually, thank you, Abhay sir. You can mute yourself. Abhay sir also gave a very crisp reply. So, my dear friends, I want to confine my answer to fix some domains so that we can deliberate something. Okay, let me share once again my screen. I will not be answering all these questions. I want answer from you people. So, this is my reply. Uh, I hope many of you might have written. We are talking about chip design. We are talking about system design, foundry, assembly, and testing. One of the speaker, one of the participant told about this display, packaging. Okay, these are different domains, but usage of machine learning and AI is still missing here. This is what we are going to decimate in this FDP starting today. I hope I have seen the schedule made by Dr. King, and there are many speakers who will be deliberating their detailed concepts on AI in chip design, IoT in chip design. Means the component, the application will be the computer part. Sorry, the technology will be the computer part, and the application will be the electronics part. So it's a interdisciplinary sort of areas which we are going to work in this FDP. So let us move forward now, my dear friends. Let us start this. Let us move this session with technological evolution happening with the human mankind. I remember I bought my first mobile phone in 2001, and it was a CDMA mobile phone. All of you might be remember that mobile phone which in which there were certain buttons on that mobile phone. And talking about the 1980s era, the phone was walkie-talkie. Again, the new technology came 2G, 3G, 4G, and nowadays 5G is a very common thing for all of us. Never around 20 years we have never imagined that there might be certain thing called mobile. In fact, I have used pagers. You do you remember pagers? Means in the coming years, machine learning and AI will be incorporated in semiconductors to improvise their performance. Okay, there is a small cartoon character showing here that a child coming to his or her mother and saying that, mom, tell me when I was downloaded. Maybe the coming years our kids will keep on asking, and the parent will have to tell that you are not downloaded, you were born. So this is a changing technology evolution happening with mankind. Okay, coming next here, this is a small hype cycle. Why I'm going to show here? Because this hype cycle will be going to tell you what key technologies we need to continually innovate with the AI while we are shifting from uh, starting years to the till now. Although this is a 2023 slide, in the next time I will in the next slide I will show of 2025, because 2026 has just started. So initially, coming back to the 1950s era, the first principle of the AI system started. It moved again to the multi-agent system, neuro-symbolic AI, casual AI, AI simulation, AI engineering. Why I'm telling you, my dear friends? Because never, even for the last 2 years, when I started working on AI machine learning for some research component, and I was fascinated to know about that very less research has been done using AI and machine learning for the semiconductors. Still, you can see here AI, decision intelligence, artificial general intelligence, prompt engineering. These all are the different domains of the AI in which started. And nowadays, a term is very popular called generative AI. And maybe in the coming years to come, we will be having some intelligent applications made with the help of semiconductors, but their performance will be judged by with the help of machine learning and AI. And coming to the 2025, the next areas might be foundation models, synthetic data, edge AI, generative AI. I don't know about foundation models and synthetic data, but generative AI is one thing which I teach also. So this is cycle is telling that how AI keeps on changing, starting from the 1950s to coming to the 2026. A big gap of 76 years, and a big duration of 76 years, and it keeps on changing. It will not stop here. Okay. So, my dear friends, if somebody is not from the computer background, although you people might be learning or using AI many times, but even the basic definition of AI has different meanings. AI is automation of the activities that we associate with the human thinking, activities such as decision making, problem solving. Someone else might be saying that AI is the science and engineering of making machines intelligent. Now, Abhay sir might be saying that AI is some exciting new efforts to make computer think machine with minds. Ravi sir might be saying that AI is the study of the computation with which we want to perceive, reason, and act. So these all are definitions of AI. Never a single time here something has mentioned about the specific application corresponding to the semiconductors, because the application of AI when started in robotics, I have never imagined that AI and robots could be a same domain. Around 2 3 years back, this has got very popular. Okay, now it's a very common thing. And similarly, in the coming years, when machine learning will be started using to this, we will classify this MOSFETs and these VLSI circuits. You people will also imagine that some tools or softwares are able to analyze the performance of this MOSFETs. I will show you tomorrow that thing in my another lecture. So, how artificial intelligence system generated? How artificial intelligence system is totally talking about. Artificial intelligence mean we want to learn from our experience. We use the learning to reason. We want to recognize images. Say, we can tell a computer can very easily tell that whether the image is of cat or a dog, which we generally teach in image processing. AI, with the help of AI, we can solve complex problem also. AI is can also help you to understand language. AI can also help you to create perspective. Then why or how machine learning or AI, they both are interchangeably used. So don't worry about these two terms. They will be interchangeably used any time. So these are different domains of the AI system where we can use them. Now, another question comes in my mind here is that why are this next generation semiconductors, means the semiconductors which are going to be developed in the next 2 3 years, they are increasingly dependent on this data driven techniques. See, my dear friends, AI and machine learning are totally data driven techniques. You need some data, you need some processing. Now, if a person is from a core electronics background, he might be having some data. Now, my question here is, why are these next generation semiconductors, mean the semiconductors which are going to be developed in the coming 2 3 years, why they want to incorporate with this data driven techniques? Any answer? I don't have my answer here, so I'm stopping the presentation for few seconds again here. I'm writing the question in the chat box, but I want anybody should reply here. Now, my dear friends, let us confine to this question now. Let us discuss this question. Please don't consider the presentation to be a single way, because whenever I give my presentation, I try to find out certain questions through which the audience could interact with me and provide me also something useful, because I am also a teacher like you, and Abhay sir seems to be very senior than me. Many of my friends in this FDP are quite elder than me. So I also want to learn from each other, all of you. So my question here is, why are next generation semiconductors increasingly depend on the data driven technique? Why machine learning and AI is the most sought out? Yes, Ravi sir, increasing complexity, PP optimization is a very good reply. These semiconductors are very complex devices. A lot of ICs are attached here to attain precision in designing devices. Please other also respond. Otherwise, only Sangeeta ma'am and Ravi sir and few other speakers are participant are interacting with me. If you're listening this lecture, if you're going to attend this session, please, I know I might be boring for some of you people, but whosoever is listening to me, kindly reply. Sangeeta ma'am has replied, to attain precision in designing devices, they aim to achieve the desired goal within the stipulated time. Uh, Sangeeta ma'am, we are not talking about the real time. So time, I think, is not a big concern for us. Okay. Current Avinash sir is saying, F, uh, fully programming SI, current day chip engineering widely dependent on program. Yes, sir. Avinash sir, I agree with you. New capabilities. Ravi sir, which new capabilities we want to explore? My question is that concern. Why data is a big concern for all those stuff. Uh, Sangeeta ma'am has mentioned something about complexity, but time was the not big concern in this aspect, because traditional physics only and rule-based approaches are no longer sufficient to handle today's scale complexity. Okay, my dear friends, I make some consensus here that we are talking about, yes, memory, computing, efficiency, complexity, all those things which are. I'm going to tell you one joke now. Suppose if you tell one joke to a human being will laugh. Do you remember? All of you watch Kapil Sharma show. I hope if you are able to. Uh, uh, King sir, do you understand Hindi in your state? Do you watch Kapil Sharma show? Anybody?
No, sir. Very few know.
Okay, but do you understand Hindi? Do you understand Hindi, or do you something?
Personally, I don't understand, sir.
Okay, so let me tell you one thing. It is something on a lighter note. I want to say that uh, if you listen to a Kapil Sharma show, he plays some joke and we human being keep on laughing. Okay, and same joke, if a machine try to understand, machine will not laugh. Okay, this is one scenario. On the other hand, if I give a uh, there is no book kept here. If I keep a one big book in front of me, okay, and I tell someone to read that book, that person will not be able to. But on the other hand, if a robot is sitting with me and he or she keeps on reading the book, in a second, in a few seconds or in a few minutes, that robot will grab all those things. So this is the difference when we are going to use the data. That book is a very big source of data. Okay, human beings has some emotional content, but human brain cannot perceive the big data. That's why the term is called big data. We need to meet the design window of the VLSI design, which is very narrow, and sharing the time frame is a big challenge. Okay, manufacturing cost for high yield processing, we need data driven. Anjali ma'am, please I want to give you a virtual clapping here from my side. My dear friends, data is getting big, speed is getting large, processing is getting slow. If we don't involve this machine learning techniques, the process will be, the performance will deteriorate. So, my dear friends, you all have replied a very good factual answers in this to this question. Let us come back to the presentation again. So please keep on responding. Because it is also a knowledge gaining from me also. My native language is Hindi. I can't speak Hindi here. Otherwise, could have told you some jokes of machine and this human being very easily. Okay, so let us move forward. So that was a very good answer by many of the participants. Let us move forward now. So, my dear friends, you might have heard about AI, but I hope you might not have heard about these terms. There are different types of AI. One is called artificial narrow intelligence. One is called artificial general intelligence. And when we apply these things in our application, the meaning get different. And third term is artificial super intelligence. I hope this will be a different thing for all of you. Artificial narrow intelligence means a machine intelligence that does not replicate human intelligence or efficiency, but merely copies it. All of you might be having Siri at your home or Alexa. Uh, I hope somebody of you might be using Alexa to play songs, to play, switch on the light, to switch off the light. That is artificial narrow intelligence. Means something fixed task is to be done. It just stimulates some specific task. That is ANI. Please tell your students also about these things. Next is AGI, artificial general intelligence, a machine with the ability to apply intelligence to any problem rather than just one specific problem. Okay, means having some good cognitive abilities. Please listen to this carefully. I will ask you one question again here. Third is artificial super intelligence. Artificial super intelligence means the intelligence that is much smarter than the best human brains. Means the scientists, the researchers in practically every field. Hypothetically, I don't know who is very intelligent than human beings, but still, if they got more intelligent than human beings, the consequences can be bad. In that case, you might have seen some movies like called Robert of Rajnikant. King sir, have you seen that Robert movie? It might be available in your native language also.
Yes, sir. Yes.
You have seen that was artificial super intelligence, means the machine become more smarter than the human being and he starts some sort of destruction. I hope you have seen that movie. Now tell me one thing, which of these AI can be incorporated in semiconductors? Any idea? It is just a question for me. I also don't know this answer. Any idea, please? Can somebody unmute yourself and reply to this answer, or you can write in the chat box as well. It is just a tentative answer. It might be somebody's. I want to see. Can somebody reply? What sort of AI can be used in semiconductors? AI, AGI, or ASI? Although these terms might be new for all of you. But any just reply. Okay, let us move forward. This was a reply which cannot be judged by somebody's answer. It varies from person to person. So, my dear friends, let us talk about the evolution of AI, that how AI started and how AI is going to now end up for the semiconductors. It started in the year 1950, where some paper was written about the possibility of the machines with some intelligence. And then a conference was held at Dartmouth, organized by John McCarthy, who gave this term called AI. And now AI term is a very common term for all of us. And in fact, the engineering jobs are getting disrupted by AI. Please ensure that this PPT is not made by AI. It is strictly made by me. I have not used Chat GPT because Chat GPT sometimes it doesn't provide the relevant. Also, it's a very good tool, but sometimes the things might not be relevant for this FDP. So I have used my brain and my concepts to find some relevant facts and figures for this presentation. And coming to the year 20 to 2010, I'm skipping the in between years. 2010, 20, then Apple was introduced, then deep learning was introduced, then Facebook face detection techniques were used, then Google self-driving cars. Recent in India, Tesla showrooms have been opened. So they all are using this. In fact, any area of the mechanical or some machine design, semiconductors are very readily used. And all these new age cars or new age vehicles or new age devices will be definitely using AI. And for AI, they need some data. They need some data processing. And for the data processing, we have some machine learning algorithms. Okay, so to, the our task will be to optimize the machine learning algorithms, and the data will be of that semiconductors. So tomorrow I will show you some visual concept as well as some mathematical values of the semiconductors data, which we can use and incorporate to get some relevant output which can be used for some application. So my dear friends, let us move forward now. This was artificial intelligence, how it started in being useful in many domains like travel, tourism, like construction, education. Now the leading sectors are high-tech telecommunications. Okay, that high-tech telecommunication is a purely electronics field. So you can imagine that the percentage adoption of this AI, starting from a small domain like construction, education, or consumer package or healthcare, have moved towards now financial services, high-tech telecommunication. Do you remember financial services, that our Indian stock market is a very big market, and all the data is being operated at a real-time system, and that data is a very huge number. If somebody is investing in stock market, he might be knowing that the values of the shares keeps on changing every microseconds. So that huge number of data processing, we need some artificial super intelligence type computers. And if those application can be used in semiconductors, then definitely the our superconductors, our semiconductors will be the new age driven semiconductors. So now there is another small question I'm going to ask here. Could a machine be conscious? That term is called artificial consciousness. I will reply this question, but just understand this question. Could a machine be conscious? Uh, the reply is, uh, what is the difference between pretending to be conscious and actually being conscious? Now, uh, what happened here? There is a small animation shown here. Uh, if a robot told you its life story, look hurt when you offended it, and laughed at your funny stories, would you think it was conscious? How could you tell? Now, try to imagine a scenario. We are praising a robot, that this robot is doing this task, this robot is doing this task, and robot is very thankful to all of us. But on the other hand, he know I am an artificial object. My intelligence is not real. My intelligence is artificial. In a similar fashion, if a robot tell you its life story, that how it was developed, how it was made, he or she might be looking hurt well when you offend it, and you may laugh at the funny actions that robot is doing to deliberate his stories. Would you think that the machine was conscious? No, machine was not conscious. Machine was pretending to be conscious. Rather, the machine was not intelligent. It was artificially intelligence. So this is a very complicated concept which I have explained through this small cartoon character. Now, there is another term. Are there some tasks which cannot be easily be automated? If so, what are the limitations? Now, how do the computer abilities compare to that humans? In fact, now the time is coming that machine are starting thinking like us, and whatever the super intelligence we are going to use in making these semiconductors, we not might not be knowing their consequences on the mankind. That movie Robot itself have told that something, that if machines started thinking like human brain, they might be acting like a disaster for the human being. So this is another concern area for all of us. Although that was a movie, but in the real life we don't know about that, something which cannot be predicted till now. Now, can machine thinks? If do you think machine can be thinking process. Machine doesn't think. Machine have the artificial intelligence done by semiconductors, done by programming the chips. Okay. Now, my question here is, what could be the difference between the traditional semiconductor design and some AI assisted design? Although you people might not have used AI, if anyhow somebody have used, he or she may be able to reply this answer. But this is a very good question, which can deliberate, which we if we deliberate for the next 1 minute, it will give you idea that how traditional semiconductors. I did my BTech in 2000. 1997. Sorry. When I started, I studied electronic devices and circuit. Uh, and at that time, the traditional semiconductors were in place. And nowadays, after a span of 30 years, almost 30 years, I did my BTech. So this is a this is a question which I want from the new age partners in this FDP. What could be the difference between traditional semiconductor design and AI assisted semiconductors prevailing today or might be in the future? So, my dear friends, can you reply this query? I want some reply for the new age participants who are doing some research in this AI. It will be better optimized with respect to silicon area process optimization. Okay. Anybody else? It will be better optimized with respect to silicon area. Ma'am, can you tell about traditional, what was in the traditional semiconductors and what could be in the, you reply about AI. What was in the traditional semiconductors? Anybody else? I'm just asking Sangeeta ma'am. Others, please also respond. Test bench can be designed precisely. Okay. Anybody from computers background can reply something about AI, how AI can be used for system design. No chance, yes. Chances of error are very less. Palvinder gave a very good answer because AI, something data is when some sort of a data cleaning or data pre-processing is done, the chances become very less uh, to when we design the AI-based semiconductors. Ravi sir is still, let me see all the answer. They're coming very fast pace. Manual design versus having previous image of design used for prediction for use saving kind. Iteration required for optimizing can be reduced. Okay. Okay, this was a good reply from all of you. Let us come back to the. My motive is not to judge your questions. These are questions which are created out of the box from my mind, and I definitely have not added the answers because I want the answers from the audience itself. So it's a good. You please keep on interacting. For the next 30 to 40 minutes, we will be discussing something more about machine learning, something more about AI, and I will also tell you a small case study if the time permits before the next speaker arrive. So please be tuned. Let us move forward now. So next comes a term called the Turing test. My dear friends, if somebody is from not the computer background, he might not be aware of this term, but this is the term called Turing test. It's a test to empirically determine whether a computer has achieved intelligence or not. In a Turing test, the interrogator must be determining which respondent is the computer and which is the human being. And this is a new term here. Why I'm telling about these terms here? Because these all are part of the AI. And when we are talking of the different stages of the artificial intelligence, stage one is, I told you in the start of my lecture, machine consciousness. Stage two is machine intelligence. Stage three is Siri, Alexa, or Cortana. These all comes in machine learning. Because in the coming lectures, many of the speakers, they will not be deliberating about the basics of machine learning. Dr. King has discussed the complete schedule with me, and I hope we have told all the speakers to touch the practical aspects of IoT, touch the practical aspects of AI. In fact, I will be touching the practical aspect of machine learning tomorrow. So this today's session is all about the basics of machine learning, how machine learning is going to put their steps in the field of semiconductor industry. Now, currently, the technology is at stage two. We are talking about the machine intelligence now. Now, what is the minimum requirement for a system to be AI enabled? If we are going to use the AI for the semiconductors, some of these areas can be useful for those application. One is AI itself. AI is a term here. I mean, building the system that can do intelligent things. We all use microwave oven. We use all this washing machine. They are all that embedded systems based devices. Next is the natural language processing. We need to build systems. We need to use make the semiconductors in such a way that they can understand our language also. It is a subset of the artificial intelligence. Some sort of chatbots you might have seen many of times. We want some sort of machine learning that can be useful in semiconductors. Uh, it is also a subset of AI. I will be keep on changing this term MI and ALI. And another term is called neural networks. It is biologically inspired network of artificial neurons, might be used in semiconductors. And another term is called deep learning, in which the data set is very big. It is a subset of machine learning. So natural language, knowledge representation, automated reasoning will lead to machine learning. And in machine, we have that complete data of that particular device, particular VLSI circuit. And based on that, the particular values of that circuit, some sort of optimization can be done to improvise some application or to create some application. Okay. Now, there is another term which I will discuss here, natural language processing. With the natural language processing, we need that's we are talking about Siri or Alexa. Siri or Alexa is completely based on the semiconductor chips or ICs used in that Siri or Alexa. They might be completely based on this automated speech and automated text writing. The person speak that Alexa switch on the light, switch off the light, on the fan, doing something stuff, means it is going to understand what a human brain is going to perceive, and the semiconductors or ICs programmed in the Alexa or Siri, they are able to perceive the natural text and able to perform some desired operation. And that for that purpose they need a huge chunk of data, that so that the computer will able to Alexa is a sort of computer only, the robot only, based on some natural language processing, and it's able to perform those tasks in a very speedily manner. Okay. So the terms, the tasks which are included here are called automatic summarization. A lot of texts are to be created in for that data, and another is machine translation, because machine is not going to understand English. It is going to something understand the language which we can say digital language or some machine learning language. So we need to have machine translation also here. We need to have automation automatic summarization also here. Now, another thing is chatbots or automatic intelligent agents. These are very popular in AI also. So, these are a computer program you can talk to through some messaging apps, chat windows, or voice calling apps. And these are intelligent digital assistants which are going to resolve your task in a very consistent manner. Now, another terms come here is man versus machine, or another term is called man plus machine. Machine is made of semiconductors or ICs or integrated or VLSI circuits. Now, if a human and a computer both read a single page of comedy, they both are watching Kapil Sharma show. I am also watching Kapil Sharma show. This is a computer is also watching a Kapil Sharma show. Okay, I am watching the Kapil Sharma show and I am smiling at my face because that's the comedy for me. But for a machine, it is doing nothing. But on the other hand, I ask if we ask both human and a computer to read 200 million pages, say we ask that Amit read 200 pages, 200 million pages, not 200. And if I ask this computer also to read 200 pages, the things are changed. The human will not be able to know when to start and when to finish. The computer will be going to win this game, because computer has a lot of processing power in it, that the complete data of 200 pages, huge chunk of data, which I asked in my previous question, that how data driven techniques are going to assist semiconductors, that huge chunk of data are easily going to process by the machine learning algorithms which are being incorporated in this computer. Okay. Now, coming to this driverless car also, the automation is created in such a manner that in case of this driverless cars, they are when the autopilot mode is on, with AI will be performing certain tasks, while human being get a lot of tension when he drives in a very rushy area or a very high traffic zone. He has to keep on he has to be very attentive all those things. But a machine which is made of some good semiconductor program with machine learning, all the things are fed in it. The machine can very efficiently drive in a very high congested areas also. So this is man plus machine or man versus machine. Okay, this is another concept which I'm telling you here. Now, in the future, We will see the rise of more collaborative workforce. We need the rise of automated automation technologists who will have a deep subject matter on some cognitive computing science and social robotics. The jobs areas where this will grow, we need some data scientists, we need some data analysts, we need a person from the electronics background who have a good hold on semiconductors. I am a person from a computer background, and Dr. King is a person from electronics background. I will tell you, sir, provide me the data. He will extract that particular data from the semiconductors, and he will provide that data in the form of an image, in the form of some mathematical values to me, and I will use my machine learning algorithms or AI-based algorithms to optimize them, and then we can create some application which may be useful to the human mankind. Okay, so it is not about destroying the old jobs, while we are going to create new jobs by working with the interdisciplinary fields. That is what Semicon India, which started in the November 2022 by the mission of the government of India, where they want that future proofing of the semiconductor industry. Okay, okay, let me ask some general question. Let us have some now bit relaxing mind. Can you name some movies where AI is used or AI and semiconductors are used? Can somebody tell? This question, I hope many of you might be knowing. Uh, Vijay Kumar sir, don't worry, feedback form will be provided. But let us come back to the this reply. Can you say something about? Can you name some movies where AI, or my question is AI in semiconductors is used, robotics is used? Anybody please reply. I am not bit fast. Is my voice audible, King sir? Can you name
Yes, sir.
some
Yes,
movies?
it's
Okay, okay.
audible.
Can you name
Yeah.
some? Okay, okay. Yeah. Can you name some movies where AI based semiconductors are being used or AI and robotics is used? I think it is. Uh, Ram, Ramani Kandan, I'm not from South India. Enthiran might be some South Indian movie. Okay, I not might be sure. Okay, anyhow, can you something some movie about a Hollywood movie or some Indian movie, some North Indian movie, Hindi movie, all James Bond movie? Yes, ma'am, all James Bond movie. You have seen that Cars also. Sangeeta, ma'am, you saved my answer. Iron Man is a very good movie. There is a movie in played by Dhanush. Dhanush is a South Indian actor. The movie name was called Ranjana. Have you ever heard this name, Ranjana? Chips enabled. Yes, uh, Terminator. Do you remember Terminator? Ranjana is a movie. Terminator is a movie. Okay. Other Iron Man is a movie. So, my dear friends, why I'm telling this question to all of you? Please, anybody else can reply. Otherwise, we'll come back to the presentation. Transformer is a very good movie. I've seen also. I've seen Iron Man also. I've seen Terminator also. Uh, so whenever I'm very fond of science fiction and this technology-based movie. I don't like Indian traditional romantic sort of movies. I love to watch scientific movies and some adventure-based movies because those things add. Avatar is a very good movie. Electric State, Devashri, I don't know. I might not have seen. I will give this screenshot in my computer, and I will definitely watch this movie. Avatar is a very good movie. So, my dear friends, why I'm asking this question, that if the film industry is using, although that's a fiction only, that is not in the real life happening, they are being incorporated. The movies reflect our future. The things which happen in our real life are being depicted in the future itself. So these movies, we have never got the idea about this augmented reality, virtual reality, or Terminator, or some robotic movie like Robot also of Rajnikant. So all such movies give some idea that what sort of things can be done in future or the perceived future. Although they all are fiction work, yes, Avenger also. I alerted all the participants now with because many new names are coming here. So thank you all of you for being interactive and writing a lot of movies names here. Let us come back now again. So, my dear friends, these are some pics of the movies: 2001, Space Odyssey, Terminator, Galacta, Robert, etc. And this are the some movies where semiconductors and AI are very readily used. Now, what is being expected in 2026? Current year, January is going to be ending now, and what are the things which we people expect from this AI, robotics, and semiconductors? Robots have entered our houses for personal use. We are going to use sensory devices. We have self-driving cars. Recently in Maharashtra, Tesla has opened their showroom, and if your budget allows, you can buy the self-driving cars also. They cost around rupees 70 to 80 lakh the first model, and our this film actors will definitely be purchasing them, or the picture or the persons who are having their good budget of buying 70 to 80 lakh cars. So 3D printing is a very commonplace. 4D printing is gaining this acceptance. So these are things which are going to happen in this year. So AI is going to continues these all steps from starting from the early artificial intelligence, which was created the excitement, moving towards a machine learning and moving towards a deep learning will drive the AI boom. And the government of India is very now energetic towards the semiconductors industry. Can you name some semiconductors industry prevailing in India? You can write the chat box also. Many of my friends are from the. Can you name some semiconductors industry in India who use this domain? I'm taking the presentation for a pause for few seconds. Can you name some semiconductors industry who are working in India for the AI assisted domain, AI applications? Anybody? Otherwise, I will tell their names. I want the names of the industries. CDAC. CDAC is very. Janisha ma'am, do visit to plan CDAC someday in Punjab. It's in Mohali. Okay. I have been going there. AMD. Yes, CDAC, AMD. One was SCL. Your next speaker is from SCL Mohali. Jattana sir is a very, very renowned name in the field of this semiconductors, and Dr. King has managed. He's a very high status than me, and I know personally him because I have also called him to our college, and in fact. I want his lecture to be first, but anyhow, he was not available at 6:30 today. Anybody? SCL Mohali, another company is Keynes Technology. Keynes Technology. This is another company in India. NetWeb Technology. Another is CG Power. So, my dear friends, these are companies which are very popular in India, working in the field of semiconductors. AMD and CDAC, SCL Mohali, Keynes Technology, NetWeb Technology, CG Power, and another company is forgot the name. MOS something. Uh, ST Microelectronics. Let me just check 1 second. I know that one of the name of the company is because these are companies you can check their profile. You can plan some sort of educational visit to them if your logistics and other uh, things
But
allow.
Amit, see, I mean, the synopsis and cadres, I mean, they are kind of world champions in EDA tools. They themselves wants to be AI integration.
Okay, that's a good thing, sir.
I
You
mean,
means our
because the
yes,
RTL to GDS to flow, I mean, from front end to back end, integrating AI with front end to back end is not so easy.
exactly, sir.
AI
That's
has
why
gone in every field, but semiconductor is very difficult.
yes, sir. Other companies
So
are
the company, I mean, company like Synopsys and Cadence they are looking for AI integration. So that means we need to, it's a very good field,
sir.
just to complement them.
Yes, Abhay sir, I want to add one more thing that the Ministry of Electronics and Information Technology they has launched their this India semiconductor mission with 10 billion US dollar commitment, and now these companies are getting some program link incentives that the government will provide some sort of funding to them through which they want that they should use AI and semiconductors, AI and machine learning in constructing these semiconductors. This
Yeah,
is all
very true.
this is yes, PLI. and this is all towards this Make in India. Our government of India is now very visionary nowadays. They want to boost this PLI program, product link incentives, through this Make in India project, and they are supporting. In fact, I will give Dr. King in the next lecture. Dr. Jattana will be coming. He is one of the member of the MIT, Ministry of Electronics and Information Technology. He will definitely tell you about some funding opportunities also. Okay. Do remember to ask him certain this question also, that please provide the participants about some MIT funding opportunities which can be readily available for the semiconductors. Okay. Please keep in mind this question. Abhay sir, you can also ask that question from the next speaker. He's a member of the MIT.
Yeah, yeah, sure, sure. Thank you.
Okay. Okay. So let us move forward now, my dear friends. So So this is something about machine learning. I just want to give some brief idea. If somebody people are from the computer background, because my next tomorrow's session will be on typically on machine learning classification of semiconductors using a tool called Orange. Orange is a machine learning tool, while the application will be on the semiconductors, in which I will discuss about this supervised learning, unsupervised learning. My dear friends, I'm not going to teach you these technologies, because all of you are very well aware of these names, but just to tell something about supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is something learning with labeled data sets. Unsupervised learning is discovering patterns in the unlabeled data set, while reinforcement learning is learning based on feedback or reward. You can use any of this learning based on the application you are going to design for the semiconductors. Tomorrow, I will be using supervised learning. I will discuss supervised learning based on some data set of MOSFETs. Okay, let us skip deep learning. I want to take you now to the uh, okay. Now, this is another question of concern. I have been talking about from the last 1 hour. I was talking about that we will be using AI and ML for semiconductors. Now, this is another question of concern for me. What could be the data security and IP challenges if we start incorporating AI and machine learning enabled semiconductors ecosystem? This concern has not been addressed anywhere wherever I read here, but I want some reply from all of you, that give your ideas, that what could be the data security concern, what will be the security of the data if AI and machine learning technologies are being used in this semiconductor ecosystem in the next 2 to 3 years. Abhay sir, can you give some input here, or anybody else also? My dear friends, let us discuss this question. This is a small IP. Okay. Somebody
Yeah,
else could reply.
actually, am I audible, sir?
Yes, 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 sir.
Yeah. So it's actually very good session, Amit sir.
Thank you, sir.
See, we just to update all of the participants over here. We had in Pune. I am from Pune. We
Okay.
had a VLSI design conference this time in Pune.
It happened around 2, 3 weeks ago. One of my friend
Yeah, yeah,
called
yeah, yeah, yeah.
Dr. Balwinder Singh might have attended from Mohali, CDAC Mohali.
Uh, I don't know, but yeah, he might have. Sorry.
Okay. Because it happened around New Year, I think. He
Yeah,
has
yeah.
used
Actually,
some
yeah,
photos
yeah.
in his
Five, six,
status.
seven. Fifth,
Yeah,
sixth, and seventh.
yeah, yeah.
Yeah. So this time I could see that. I mean, generally I used to attend this kind of conference, VLSI conferences every time. But
Okay,
this time the response was huge, tremendous. The reason is the way we are growing in semiconductor. That's the only reason.
okay,
Second thing is most of the companies that I mean in Semicon also we also participate. I mean as a institute we all participate in Semicon. We
okay.
participate in VLSID also, and we could see that yes, AI integration or ML integration with semiconductor is one of the biggest challenge because
That's okay, okay. I'm
yeah, tell
listening.
me sir, tell me.
No, no, please keep on continue.
Yeah. So We are as an institute, our students, our faculties are also working on it. Many of the semiconductor companies are also working on it. But just to kind of update that, yes, we need people, we need professionals in this, and we need to kind of integrate with the computer science, maybe AI, ML with semiconductor.
Exactly, exactly. Abhay sir, at the end of my session, I will give you some idea also, although you are quite
Yes, sir.
senior than
Please.
me. But definitely I will give some case study also. The thing is that the government of India wants to reduce the dependency of the semiconductor industry on Taiwan and Japan. Uh,
Yeah, yeah,
I
yeah.
Yeah, now you have seen Trump is forcing a lot of tariffs on India, and I'm very fond of stock market and economics also, and I was
Mm-hmm.
watching the economics today, and in the
Mm-hmm.
coming budget you might not be surprised if India is starting impose tariffs on US also. It might happen now because
Why not?
India want to reduce their dependency, and the government of
Correct.
India want these such brains should come up, and they are providing this 10 billion US dollar boosting. That's Ministry of you can search in Google also, that Ministry of Electronics and Information Technology. They are finding some program link incentive to these
Mm-hmm.
industries. These industries are going to be benefited a lot from these PLIs, this
Yeah,
PLI
yeah.
incentive.
Very true.
So if any of the friend is going to invest in semiconductor industry for the next 2 3 years, he or she will be getting a very good return. In fact, I generally invest in future the stock market also. So I keep on I'm having two stocks in my kitty related to semiconductors also, because I know semiconductors is the future of India.
Oh, that's great.
The Yeah, okay. Now, recently, Apple also might be going to start test. Maybe the other companies in which the export also, which is happening from Taiwan and Japan. The Modi government is very now. They are very eager to reduce the dependencies of semiconductors on Japan and Taiwan also. So
Mm-hmm.
maybe the coming years, the research component will be very high in our country also, and the program link incentive which government has started giving to this industry will definitely boost their production. And
Yeah, that's the
I hope.
reason Tata is starting that 28 nanometer fab in India.
Yeah, exactly. Sir, there is a one city in Gujarat, Sanad. Sanad. I'm writing the name SANAD. Sanad,
Mhm.
where the semiconductors are also going to be manufactured. You can Google it. If I might be not the name might be wrong
Oh,
here.
okay.
Uh,
Okay. No, no.
so
As
these
far as my knowledge goes, currently all the fabs, I mean, not fabs, the wafers are coming from China.
No, the first I forgot that size of the nanometer. This size where this Sanad industry in Gujarat is going to make. Let me tell you once. Just I'm going to
These are
Google it
all
also.
OSATs, sir. These are all OSATs. Oh, new
Yeah.
fab that we.
They, that is a one of the first OSAT industry is going to be open in Sanad in Gujarat. I will tell you tomorrow. I'm tomorrow also having a lecture.
Okay,
I will
okay. We will
definitely tell.
discuss. Yeah, yeah.
Okay.
Okay. Yeah.
Okay, my dear friend.
Thank
Let us
you.
move forward now. Thank you, sir. Yeah, also all incentive are available for 20 nanometer technologies. Sangeeta ma'am, I'm not be sure about the size because, but the government of India is providing good incentives, this program link incentive for this. That was a OSAT facility, definitely, which is acknowledged by Abhay sir also. So, my dear friends, this was a question which was good replied by participant also. So, I having only 5 to 10 minutes, I'm going to start with one another presentation now. I'm going to skip the slides for few seconds now. I'm going to please just wait for few seconds. I'm going to tell you what case study here. Somebody please confirm, is it visible?
Yes, sir.
Okay. Okay, my dear friends, since I'm having only 10 minutes now, I want to wrap up my session with one case study that how this whole process can be feasible. See, semiconductor is not a simple cup of domain that I come and show you that how it is being fabricated, how it is being developed, how machine learning will happen. Rather, I have also started working because I am a person from the computer background, and around 2 years back when I started, when my college principal told me that Amit, start incorporating interdisciplinary areas in your field, because we also try to seek some funding from the government of India based on some RPS scheme or some this ANRF grants, in which the government of India provide funding to those cases only which are in the kitty of their development stages. They don't provide funding to the absolute research ideas. So that's why I was also started thinking, and I talked with one of my electronics professor who has done PhD in VLSI, and my PhD area was machine learning optimization. And we are thinking to send some good proposal this year. 30th January is the last date for the ANRF grant. I hope you people might also be applying. And if the luck favors and the chances and if we are able to make a good proposal, definitely we will do something relevant for the society also. So this is a small case study where I try to show the steps of integration of AI and machine learning for defective detection and yield improvement. These are the steps which you can use in some research paper also. So my dear friends, AI and machine learning techniques, it will enable the semiconductors to harness the power of data driven insights, because shortly AI and machine learning will depend on the data. We want to optimize that manufacturing process. We want to optimize the yield rates. Now by leveraging the AI algorithms, which I've told you, supervised, unsupervised, and reinforcement learning. All of you are from the computers background or electronics background. You might be knowing that algorithm like called naive Bayes, ANN classifier, blah blah. There are a number of algorithms. You can use some algorithm which is relevant with some optimization. uh, you need to identify some algorithm which excel in pattern recognition. Tomorrow I will show you small algorithms. You might have not have used that tool also, I hope. Now another step will be these machine learning models will be capable of some predictive analysis, and they can easily identify some suitable subtle defects also, because we are having a huge chunk of data. And to find out the errors in huge chunk of data, machine learning or AI algorithms are very efficient to predict these equipment failures. First step is the objective of the case study. We want why we are going to do this study here. The first step is enhance the defect detection accuracy. We want to evaluate that how AI and machine learning technologies will be able to find out the defect detection in semiconductor manufacturing process, because semiconductor manufacturing process is a very subtle process, and small defects can lead to some catastrophe or failure also sometimes. We want to optimize the yield rates also. We want to mitigate some production inefficiencies. We want to have evaluate this real time application also. So we want to assess the feasibility. These are the objectives of a particular research which we can plan to do by incorporating AI and ML for semiconductors. What are the things we desire? We need some research design. We need to do some conduct some empirical studies, because every study doesn't prove to be a successful one. So we need to do empirical studies to study the effectiveness on AI machine learning algorithms. Every algorithm is not suitable for semiconductors, so you need to do experiments again and again. Another thing, we need data collection. Data collection, suppose if you want to have some collaboration with a person from electronics background, I'm from a computers background, so we can collect some real time and historical data from the semiconductors manufacturing process. Abhay sir is a very good help to all of you. He's from that background, so he can provide you some data collection like defect images, process parameters, yield rates, quality metrics, utilizing sensors and imaging system, all this stuff. There might be some data available on the Kaggle also. I will share you something tomorrow. Another thing which we need to start is we need to select the model also, which AI model which we want to use, which deep learning model like CNN or supervised or unsupervised model which we want to use. Please make sure there is no specific model available unless and until we do research. Okay, we want to find out some anomaly detection, and next thing we need to validate the result also. Okay, as a researcher, if we as an academician, if we do all those stuff, the chances of getting a good grant also becomes very successful. Next is the implementation strategy. Okay, implementation means we need to design some framework that how we will integrate the AI and ML model into the existing semiconductor process. Since I don't have some lab sort of facility, I will be showing you all those things tomorrow with the help of a small tool. Okay, I will be having some semiconductor data tomorrow, some numeric data also, some picture data also, and machine will tell some sort of classification based on that data. So the actual implementation I will try to show tomorrow with small machine learning tool. Okay, I'm a person from computer background. My application will be semiconductors tomorrow. But to understand that tool, we will have a 1 hour session about that tool. In last 30 minutes, we will discuss about the actual implementation of that tool on the semiconductors. I hope if anybody knows about Orange, it's good. Otherwise, please be attend that lecture tomorrow. And another thing we want to is the evaluation parameters. See, unless and until we are going to evaluate the efficiency of the AI based algorithms, we want to compute such metrics like accuracy, how much is accuracy of the defect detection, how much is false positive detection rate. We want to yield the improvement percentage, and we want to improve the throughput enhancement. And then we will going to compare with them another AI machine learning approaches. You can Google it, and you will find out very few research papers are available as compared to the other trending areas of research. Okay, please be sure about the ethical consideration also. We need to adhere to data collection, processing, and storage also. And we need to, while cross validation, please mitigate the biasness also to ensure the fair and unbiased effect uh, outcomes. Okay, and another thing is we need some statistical analysis also. We need some interpretation finding also. We need some statistical analysis to validate the significance of a result. It should not be a hit and trial one. Okay, so some statistical analysis should also be there. And another thing is we want to draw conclusion about the how that AI and ML are able to interpret the findings. Means whether the outcome is a really good one or a bad one, or how much is the impact of using AI and ML on your result. And this is the conclusion of my session. My dear friends, I just gave you a broad idea in the this span of 90 minutes, because this is going to be a making a ground for the next session, because many of the speakers will be coming up and they will be talking about AI in chip design. So specifically, Dr. King gave me the lecture that we want the base of the complete FDP in your session. So you have to talk about AI, you have to talk about machine learning, you have to talk about semiconductors. I don't talk about IoT and 5G. I have spared to the given chance to the another speaker who might be coming day after tomorrow. So my dear friends, the adoption of this machine learning uh, definitely have some challenges, because some specialized expertise is also required. Semiconductors, nobody is not a cup of domain for every person. Only the expert can handle those stuff very carefully. We need this gap will impede the rapid integration and responsiveness in the semiconductor process. And in conclusion, this integration of AI and ML will hold immense potential to revolutionize the defect detection and yield improvement process. If you make a very good proposal based on this case study, the chances of getting grant in ANRF or RPS are also very good. In fact, there is another grant called Indian Knowledge System. I'm going to apply that grant also, where working on some other domain. But you can think some research area. Government of India is funding 25 lakhs rupees. How this sort of AI or machine learning can be useful for some application, not semiconductor only, but any other area you can also explore it. So the continued research and this development in this area will definitely overcome these existing challenges. And maybe in the next 5 years, we might see something useful, because around 20 years back, we have never thought that mobile phone will be something which we will be using. I was using pager in 1997 or 2001, and I have never imagined that mobile phone will be things will be coming in future. And similarly, in the next 5 years, if Dr. King again organize some FDP, and if we all are participant again here, we definitely will be deliberating that something which is very common nowadays, that AI and ML is very common in semiconductor industry. So this could be the future scope for our generation to coming here. The fully AI driven exploratory data analysis, self-optimizing chips, which are very new here, cross-layer machine learning, strong industry. For this purpose, we need some strong industry and academic collaboration. So, my dear friends, this is the things you can take to your home today. I discussed something about AI and ML. I discussed something AI and ML for the semiconductor industry, how they both are used for the semiconductors, and a small case study for the real life implementation. Tomorrow, my session will be on a small tool called Orange. In the first part of my session, around 45 to 50 minutes, I will discuss that tool, because unless and until you are not able to operate that tool, you will not be able to use that tool for in your life also. That tool will be very useful for your general purpose also. And in other part of session, I will show you some 2 to 3 examples of that using the tools for the classification of semiconductors. So please stay tuned tomorrow. Otherwise, this is the end of my session, and I hope all of you enjoyed this session. Still, if any of you want any doubt, you can ask me. I am readily available. Otherwise, Dr. Jattana is also going to join, and he's a very versatile speaker. Still, if anybody want to ask something, I'm here, and I hope all of you enjoyed my interaction with me. I kept on disturbing you throughout the session. That is my way of pedagogy to interact in this sort of online lecture. Okay, King sir.
Sir, so it's time to ask questions. Does anyone have any doubts or queries? Please feel free to ask questions.
In fact, I kept on asking certain questions, so in a way, I was getting a lot of answers to all of them. Simi ma'am.
Okay, sir. So,
Anyway,
sir, we extend our sincere gratitude for today's insightful session, and we are looking forward tomorrow's session with great interest, sir. Thank you so much for today's session.
okay. Thank you, my dear friends. Thank you, Abe sir. Thank you, King sir. Thank you, Hena ma'am, Parveen ji, Sangeeta ma'am, Shivam Srivastava. See you tomorrow once again. Thank you, all of you.
Thank you, sir.
Thank you, sir.
So I think let's start our next session. Next session is handled by Dr. H.S. Jattana, Professor MNT Jaipur. So for a brief introduction, I call upon Miss Saina. Saina.
It's my privilege to extend a warm and respectful welcome to our distinguished resource person for this faculty development program, Dr. H.S. Jattana, professor at MNIT Jaipur, with over 37 years of experience in the field of semiconductor technology, VLSI design, and advanced electronics. He began his professional journey as a design engineer at Rockwell Semiconductor, Newport Beach, USA, where he worked on the design of 65C series of digital devices. Subsequently, he joined the Semiconductor Laboratory, where he gained extensive hands-on experience in CMOS process development and integration, VLSI design, VLSI testing and characterization. As a scientist, G and
Saina, your voice is not clear.
Saina, your voice is not clear.
Saina. I think some network issue. Dr. H.S. Jatna, he has 37 years of experience and he is professor in MNIT Jaipur. So I warmly welcome sir for the session. Hello. Hello.
Jatna, sir.
Yeah, so are you able to see my screen?
No, sir. Yes, sir. Now the screen is visible.
Is it okay?
Yes, sir. Okay.
So, good evening. And as per your this program, which is mainly on AI/ML, use of AI/ML in various applications. So I will be talking about there are two things involved in this. First of all, the processors basically, which are used to run these tools, and how they are designed. The processors which are being run to design, they are designed as a digital processor. And what is the flow? As you know that any processor will have billions of gates, and one gate has four transistors and it has billions of gates, so the electronic circuit is quite big. It is not possible to do it manually, so there are software involved in doing all this. And flow is important. And the design flow, like the design steps which are used in involved in designing a digital chip. And if you see the complete flow, it is segregated in two parts, like front end and back end. Front end means writing the code, which can be a VHDL or a Verilog code, which we call it an RTL. And that code is written, which describe the behavior of the circuit, and it's in a high level language. And but that code describes the behavior in simple language. That is not the circuit. And from that you can do the verification whether that code, for whatever behavior, whatever purpose it has been written, it is doing that purpose or not. That can be verified in formal verification. And then netlist can be generated, and that netlist then is given to the backend flow. And the backend flow is as per given in this outline. So we will have the in the first step in the backend flow is the floor plan. Let me go to this second picture, which so are you able to see the second picture? So there is a front end team. They will do the you can say they will write a code. Nowadays it is or do the logic design, and finally the backend team will take over from that logic design. After that synthesis, logic design is converted to a gate level. And because it's a initially it's a VHDL, hardware descriptive language, which is English like language, high level language. So that is converted to logic gates of a particular foundry. And then that netlist is generated, and the backend team then goes to do these steps in the backend flow, which are the floor planning. There are various modules in that design, how it has to be placed, where each module will go. So that is a part of the floor planning. Then the placement, and then routing between various signals of these modules, and then the physical verification, and then the layout. So this is the normal standard EDA tools which are used. And if there is some machine learning built in these tools, that can make the exercise fast, and it can help in the design cycle. So now if you see on this, on the left hand side is a you can say the log after synthesis the circuit will look like this. There are a number of gates, flip flops, other circuit elements are there. So and but this is a symbolic representation. There are symbols used for flip flops and gates, various cells. But and then the front end will generate this, and finally this has to be converted, and finally this has to be converted into a GDS, into a layout which will look like this. There are various layers in this, and that is the part of the backend team. So the backend team, and there is a number of steps involved in this. and each step a different tool is used. So there are a number of software tools which are used, and all those tools can be have we can have a built-in intelligence in that tools. Because now, as you know, the latest technology node is below 10 nanometer, and in below 10 nanometer, the today's current modern processors, they will have close to 5 billion gates, 5 billion gates in that. And it's not that easy to do the placement, to do the layouting of those circuit. So that's why there is a standardized flow. So we will be talking about those standardized flow. So this is the flow. So we have a design. We have done an RTL design. We have simulated that design, and we found that design is okay. Then we will go with the synthesis. To do the synthesis, there are standard tool to do the synthesis, like DC compiler. It's a Synopsys tool. Synopsys is the company. They have a DC compiler. They will do the synthesis, and for that, synthesis is done for a particular foundry like TSMC or a global foundry. And synthesis tool will need the cell library details. Cell library, standard cell library, it will have lot of cells, and it will have all details, and it will take, the tool will take all these relevant cells from the standard cell library, and the timing constraint, like at what speed you want the circuit to work. So those kind of constraints will be there in that. And based on that, you will do the synthesis. After the synthesis, the logic, the circuit is now in terms of the logic gates and other modules. There might be some micros in that circuit, and for that we have to do the formal, we have to do the floor planning where each unit will be put. So that is a part of the floor planning part. Let me see why it's not moving. Okay. So we have to do the floor planning part, and after floor planning, what we need the pad positions. We need in all these things. We have to do the power planning. For that, how the IO pads are placed, how the libraries are placed. So what are the timing constraints? So all these details are covered in this block, in the placement and floor planning part. And then we will because each flip flop requires a clock, so you have to insert the clock, and there are various strategies to do the clock, and that are covered in clock tree synthesis. And after placement, the all these blocks are routed means the signals are connected. From each block there will be some signals going to the other, so those signal nets are connected in routing. And after this, there are certain other things which are like your corner pads, dummy fills, corner fills, ESD fills, and decaps, and that are included in the chip finishing part. And then the chip is ready, and then the physical verifications are done. There are a number of tests of physical verification, DRC, LVS, and all those tests are done. If all those tests are okay, then the GDS is released, and that GDS goes for the mask preparation, and finally it goes to the fab for fabrication. So this is how it is. And the backend design, the tool which does each there are two main companies in this. One is Cadence, and another is basically a Synopsys. Synopsys digital flow is quite popular, and the tool which is used in the backend of the Synopsys is ICC or IC compiler. So IC compiler, we need these four inputs. It will need your gate level netlist, which comes after synthesis tool, and synthesis tool is a DC compiler that is given, and then it needs information related to the technology file where that circuit will be fabricated. So that technology file, it will have all these detail, what are the layers, and what are the design rules, what are the RC models. So and how is the physical libraries, what is the physical details of those libraries. So all those things will be there, and if you have any your timing constraints on the clock, so those how much delay in the clock is expected. So all those constraints, they are in terms of code, in terms of script. TCL is the language which is used to write those script. Those are given to the IC compiler, and IC compiler will work on all these things in a sequence of steps, so that we will see. Technology file contains all the information about the various layers which are used in the realization of any gate or a transistors. So all the technology layers, there may be around 30 to 40 technology layers. They are numbered, they have a name, and they have an abbreviation. And like GC is a gate contact, layer number is 8, and it's a poly layer. It will have a different color on the tool. It will be shown in a different color. And similarly, active metal 1, VR2, metal 2. So all these layers will be there. So they will be shown in a different color on the tool. And then there is a TLU plus. It's basically lookup table. It contains the information about the parasitics, and like for a dielectric, which is a used in VR2. So what is the thickness and what is the ER for that? And similarly for a conductor, what is the for a metal, what is the thickness of metal? 0.554 micron, and minimum thickness, typical thickness, and all that information related to the parasitics will be contained in this. Logic library will have all the details of the standard cells. Each technology, they will give you the different standard cell libraries at different VTs, at standard VT, at high VT. VT is a threshold voltage at low VT, and each cell will have these detail cell characteristics. What that cell is doing, like it's a 2 input NAND gate, or a 3 input NAND gate, or a flip flop, or a scannable flip flop. So it will have its characteristics. What is the truth table? What is the timing details? What is the rise time? What is the propagation delay? What is the fall time? So all timing details will be given. Power details, how much power is consumed by that cell. So that information is given. Your design rule information is given. Operating conditions. Operating conditions, what is the power supply? 1.8 volt, and whether the cell works in which temperature range, minus 40 degree to maximum 125 degree. So all these things are given. So the logic library for each cell, if there are 500 cells, for each cell all this information is there. The functionality of the cell, the timing of the cell, the power of the cells, and other logical design rules. The fan out, what is the maximum load it can drive, and all that information. What are the capacitances? All that information is provided of that cell, and of that basic cells. Besides the standard cell library, there are in a design there can be some hard macros. Hard macros means which are bigger circuits, like memories. So memories are a bigger circuit. So those things are given, like PLL may be there, voltage regulator may be there. So they are called hard macros, and they are not standard cell. They are much bigger circuits. So those, for those also all this relevant information will be there. So this is one example of a basic cell, which is an inverter. So this diagram on the left hand side, it shows all the layers which are used in making this cell. You can see different colors are there. That is why all the layers. The upper transistor is a PMOS. This is where I am putting my cursor. It's a VDD. This is a VSS. You are able to see this is a VSS. It's in blue color. This is also in blue color. Red color is poly gate, this red color. This is P transistor and this is N transistor. Your gate is connected. This is here the contact is being made. This is a squarish kind of contact, and a blue metal is put. This is a, you can say, topmost rectangle which is blue in color, that is a contact. Now on the upper side, this is a VDD and a metal line is blue in color, and the drain is connected with this. This is the contact and this is the drain. This is the, and this is the connection for the drain, this square. So here drain is connected and this also drain is connected to VDD and this contact is showing. This is the source. This is the connection of source. So like here also this is the drain. This is the source. This source is connected to VSS, and both these drains are connected through this line. This yellow, both these drains are connected, and then the output is taken from here. So output is from here only. So it has all these layers in this. This you are seeing, this is basically a well, this rectangle. And FRAM view is a phantom view. So it gives only the upper layer. Phantom view only, it contains only the information about one layer where the contacts have to be made. So you can see it is giving VDD where contacts have to be made, the top metal. So metal is like this. VDD, this is VSS, and this is the metal patch which we have put here to make contact with the this thing, with the source of PMOS. We have to make contact. That's why this metal is there. This line is connecting the drain of two. Here you can see this is the contact, this is the contact, and this metal is put to contact, to make contact between the two drain. So this is the contact between the two drain. This is the input contact. This is the input contact. This is the source of NMOS and VSS, source of NMOS and this. So this is the phantom view which gives only the top layer. This top layer is the metal layer. It's in blue color, and so wherever needed, it doesn't have all the layers, so it has less data. And similarly, if you have 1 billion gates, so all this information will be there of 1 billion gates. And if you have to do some placement, you need not do the placement with all the layers for the first time, because it will take a lot of data and take a lot of time. So the tool can only take the abstract view, can only use the abstract view. When the tool has to do the verification or simulation, it can use all the layers. Now design constants are important. Design constants are given by the designer. They are the constants on the clock. What are the constants on the clock? Like what is the clock signal? What is the period? What is the duty cycle of the clock? How much skew is acceptable? So this is the clock. Clock is being fed to, this is the design under analysis. So what is the skew? What is the duty cycle of the clock? So all this delay specifications of the clock or of the input, they are given, and they are given in terms of a script, and the values are given in nanosecond, and those will form the constraints. So whenever the tool tries to do the physical layout, and it will after choosing the correct gates in the synthesis, so it will keep in mind these constraints and do work accordingly. So the physical implementation basically includes all these 4 or 5 main steps: floor planning, placement, clock tree, and routing. So we will see each of these. First is a floor plan. Floor plan, as the name suggests, there are various blocks. So each block will tell where each block has to be put. Like in this example, if you see, there are 3 macros. One is an IP, this one. There is a RAM, memory, and there is a ROM. So these 3 blocks, this is the sizes of these blocks. This is the sizes of these blocks. These ROM, RAM, and IP, and other is the standard cell, which is a core area. So where these blocks will be put and where the core area will be, where the IO pads. So these where I am putting my cursor, that these are the IO pads. So where the IO pads will be. So that and how many pads, what is the exact location. So all those things are decided in the floor plan. It's just like when you are constructing a house, so you will have to do the plan where each room, bedroom will be there. Or a better example is a town planner. When he plans a town which is spread over 10,000 acres land, so he has to make a plan where the road will be, where how much wide the road will be, where the residential area will be, where the markets will be, stadium, how the power will be given, how the water lines will go, how the power lines will go, where the playground will be, what is the size, how it is the connectivity between residential area and the market area. So all those things in a town planner he has to keep in mind. In the same way, the chip designer, when he's doing the placement, when he's putting the various blocks, so he has to keep in mind, and the goal is you have to minimize the total chip area and you have to make routing easy. And so what we call it, your PPA, power performance area, has to be kept in mind. So the tool will do this. It will try various permutation combinations, which particular combination is best, it will tell you. And so ICC like tool, IC compiler, it will do various combinations of floor plan. And if there is some built-in intelligence based on machine learning and deep learning, that tool can do a better job in a lower time. And because it has some memory of a similar problem done earlier, and what was the solution if that kind of intelligence has to be built in that. And it is required for the lower nodes because the number of cells are very very high. And the tool takes a lot of time sometimes to do this. But if there is some AIML built in this, it can be made more effective and more efficient. And the inputs for the floor plan, they are basically the design netlist, which is outer synthesis, and how much area, the chip area should not exceed a particular, that will be the target. The chip should not increase a power, say 500 microwatt of power. There will be timing constraints, and there will be IOs, and how the macros are placed. The macros are those big blocks like this. These are the macros: IP, RAM, ROM. They are the micro. How their placement in the chip matters a lot. It decides the overall performance of the chip. So how they are placed to minimize the total signal nets, so that the tool will tell. And floor that tool will take these inputs and the outputs. It will generate, it will earmark the area of each, where IOs are placed, where the core area is, where the macros are placed, how the power grid is designed. So this is the power grid. Your line, red lines you are seeing, these vertical lines you are seeing, these horizontal lines you are seeing, this yellow, this blue color line, this is a power ring. And these red is a power strap. And this is the core area. So the power, how the power is distributed in that chip, so that it will decides the placement of these things. You see, the example is again very similar to a town. If in a town, if you have to build a town, it should have say 1 crore houses. Okay, so you have to lay out that. And, and for a 1 crore houses, what you have to do, how the houses will be laid out. And if 1 crore houses are there, there will be population, each house 4 people, so 4 crore people. Then there has to be provisions for school, for hospital, for playground, for market, for roads. And roads will be of different widths. And then each house should have an electricity. Each house should get 220-volt electricity, and you have to make plan for that. Each house should get a water connection, a sewer connection. So the problem is similar to that. So in a power, basically, so that there is no, each house is regularly getting 220 volt. It's not that some houses are getting 220 volt and few houses are getting lower than 200 volt. So you have to make those power network like this. So in a chip also, it's very important that each transistor is getting the required supply. And now with the lower geometries, the power supplies are falling. They are less than 1 volt, and it's very important that each transistor gets 1 volt. If it is getting 50 millivolt or 100 millivolt less because of IR drop, then that particular cell can malfunction. So there are certain guidelines also in a floor plan. Like I have placed this memory module here, but as you know, these small rectangles which you are showing, these are the nets on which they have to be connected, but there is no space here. So we call it narrow channels. The channel is narrow. There is no space. You have do the placement of this block in such a manner that there is no place left. There is no channel left. And this area you have placed these two, so that here there is a very less channel is the when you place a macro like this, on each side of this macro you have to leave some space for nets, for connections, interconnects. So if there is a less space, then there will be a constructive channel. So here maybe the space is less, so there will be a constructive channels. Okay, so all these things are considered when you are doing the floor plan for the chip. So how the power planning is very important in a chip, and it has been found of all the field failures, 40% are a result of the bad power planning. So power planning say the chip has works only on one VDD, 1 volt, and there has to be VDD and there has to be VSS. So you can see here the outer is a VDD ring. This one outer where my cursor is VDD is written. So this rectangle is a VDD ring where I am moving my cursor. So on this VDD ring, I have this. I have made stripes. This yellowish color, and this black color is the contact. It's making contact to the VDD ring, and there is a strap. Here also it's making contact. Here also this is again a strap. Here this is also again a strap. This is called strap or stripe. So after a stripe or a strap, then again I am making a horizontal line which is bluish in color. This one, this line where the cursor is there. So you can see here, this is making a contact here, black color contact is there. It is making a contact with the stripe. So the power which is on the ring, it has come to these blue line. So now this line will have 1.8 volt. And similarly VSS, the second this VSS ring, and this VSS ring is here, and then on this VSS ring this yellow is a stripe for the ground, and on this ground this blue is a rail of that ground. So this is VDD where the cursor is, this is VSS, and this is the VDD, this is VSS, and between these two all the cells will be put. They will get on the top VDD, on the bottom VSS, so all the cells will be put here in between. As you can say, the spacing between these two are same, so all the cells will be put there. Now the thickness, the width of these metal lines are different. As you can see, the rings, they are wider, stripes are less, and then rails are even less. So the designer, the IC designer, depending on the requirement of the chip, how much current is flowing, he will decide on the width of all these individual metal lines. And in a chip, there may be number of metal lines, 8 to 10. So all this power system, power grids, they are made using the top metal lines like M1, M2, M3 are the lower metal lines which are very close to the transistors. And as you go away from the transistor, those metal M7, M8 and those metal lines, they are thick metal and they are used for making these rings, stripes and rails. And in this way, this whole power is provided to the chip. And the designer has to decide about these dimensions of each metal line, and the tool will carry out the various analysis like how much current it can handle, what will be the IR drop. So based on tool will tell, the software will tell, and the designer will have to decide and fix one values. So after this, the uh, power thing is ready. Then the design challenges in this: how many power ground pins should we allocate? Which layer of metal? Generally, top layers of metal are used. What should be the width of the wires? We have to minimize voltage drops, reliability problems. So we have to maintain this VDD. There should not be any noise on this VDD VSS line. There should not be any ripple. So decap capacitors are also put. So there should not be any noise on this VDD and ground. And then how do we? So these are some of the challenges in maintaining this, making this you can say power system to the chip. And how many power pads will be there? There are certain formulas given, so we will not go in that detail. Depending on the current requirement, how many VDD on each side of the chip will be there, how many VDD pads, how many VSS pads are there. So it depends on the how much power the chip is consuming, how much area the chip is taking. So based on that, the designer can calculate this. So after doing this, the circuit will look like this. So you can see after floor plan has been done, and in the floor plan, micros are placed. These red colors, they are the micros. There are two micros, they have been placed. IO pads you are seeing on the periphery of the chip. Inner blue color, you are seeing the power grid. So all these power lines have been placed. So power lines also has been done. So the chip will look like this now at this stage. So next is the placement. We have to do the actual placement, the coarse placement of the various cells. And the tool will ask that which is doing the placement. There are three methods. Traditional method will minimize the area of the chip and the wire length of interconnects. Interconnect lengths have to be minimized. If it's a timing driven placement, it will minimize the timing, minimize the delay, like maximize the speed. And if it is a conjunction driven placement, it will ensure there is no congestion. What is the meaning of congestion? We will see in the next few slides. So the tool will ask you, you have to choose one method, and based on that, the tool will do various again permutations of placement, and it will tell you which placement uh, minimizes the area and maximizes the performance. So first of all, it's a coarse placement will be done. This is on the left hand side, there is a coarse placement. So you can see each block has been given a location in terms of XY coordinate. So it just like again an example of a town planner. Whenever on the top view, whenever the town planner does, it will earmark some area, like this area will be residential area. This area will be earmarked for parks. This area is earmarked for roads. So all area he will earmark that. And in a course placement, there is certain overlap of these, because this is not exit, this is not exact. This is There will be a certain overlap between these blocks. This is a approximate location. It might change a little bit, and the tool will first do a quest placement, and the cells may overlap. And because why? Because then it the tool will not take in doing all these permutation combinations. If the tool has to do the exact, it will take a lot of time, maybe few days. So we don't want that. So we want to do it fast. And there's another reason also for this. So it will do some overlap, and it will tell how we can minimize the area, what will be the length of the interconnects. So that is first aqueous placement is done, and once aqueous placement is done, then the final placement, legalized placement is done, where the exact locations of each cell are given. So you can see there is slight difference between these two figures. In the legalized, each cell is allocated a unique position. There is no overlap. Whereas here, there can be an overlap, and this is the exact. The cells are moved to physically legal locations, eliminates any overlap between cell during the legalized. So first a coerce is done and then illegalized. After doing the placement, you may find that certain critical paths, they are not meeting the timing. For example, in the top, this 4x driver is not able to drive this load. So you will have to do the resizing. And resizing, either you can put a buffer. I have put an 8x buffer. Now it can drive. Or I can 4x. I have separated in 2x, two buffers, 2x, 2x, and now each is driving 2 unit loads. 4x cannot drive 4 unit loads, but 2x can drive 2 unit loads, because the capacitance of 2x will be much smaller as compared to a 4x. So that may be. So one of these, or you can put a buffer which can drive the more load. So from initial placement, there may be slight changes because of timing. You have to meet the timing requirements. So in the below diagram, like initial placement, there is a change in the final placement. As you can see, there is an upsizing on this flip-flop, and there is some logic also is changed. Some logic also here, as you can see, some logic also is changed, because the critical path, it was not meeting the timing specification. So the designer has to look into it, and manually he has to change that thing. So this is the legal optimization part you have to do. And once you have legally optimized, you have to do the legal placement. Exact placement will be done after this. And if there are scannable flip-flops, scan chains are there, which are DFT, designed for testability. Later on, this design, after doing it on a wafer, when it is made on a wafer, it has to be tested. And for that purpose, scannable flip-flops are used. And this may require how these scannable flip-flops, how many chains are there, how they are connected. So there are four flip-flops. Either they are connected like FF1, F2, F4, F3, or they are connected F1, F2, F3, F4. So like this. So how they are connected, how many chains, how many flip-flops in a chain. So all those decisions are taken in this, in a scan chain handling. So you can see here, this is a good placement on the left hand side. If the placement is good, these are the IO pads. The small you are seeing, small rectangle, these are the IO pads. So tool has placed these IO pads like this, and these red lines, very thin red lines, they are the nets. So the nets are shorter. Overall, they are shorter. So there's no congestion. And there's no congestion. The total wires are also shorter wire. You need less metal level. delay will be small, power will be small. You see, if at the bad placement, you have put all the IO pads here, so you see the number of red wires are much more. So length of wire is more. There's more congestion. You can see how these wires are going crisscrossing. So that is the congestion. So there's a lot of signals going here and there, lot of wires going here and there. So that will consume power also. It will take more delay. It will take more chip area. So all bad effects of this bad placement. So that is why the tool will try various permutations, combinations, and will place all the blocks in such a manner that all these wire lengths are minimized, area and power is minimized. So there are various algorithms used, and these companies are working to make these tools AI aware, so that there is some intelligence also is built in these tools, because the number of cells, they are very high in millions, billions. So in millions of cells have to be placed, so you can see how many combinations are possible. And if tool has to try each combination, it will take huge amount of time. And so that is the reason, if some machine learning, by some algorithm, if you are able to reduce that time and do make the more effective utilization of the tool, so once you have done all these, the design will look like this. So here we have done the power, we have done the placement, we have not connected those modules, but we have done the placement. So the design will look like this, because all layers, that is the different colors are coming, because each layer has a unique color, and you are putting one layer over the other layer over the other layer. So that's how these colors will appear. And then you have to do the clock. So now clock, if this is the clock pin, this clock is going to different flip-flops. But you can see this flip-flop is near the clock pin. The clock will come early. This flip-flop is far. So there will be a skew in this. The clock will be delayed at this flip-flop. But we don't want this. Then there will be a clock skew, and it will result in malfunction. So how to do? We want all these yellow buffers, all these yellow flip-flops or cells, they should get the clock at the same time. Okay, so then this is the clock, you have to use buffer. So this is the clock, I have used a buffer, green buffer. So this green dotted line is going there, and then I have two blue buffers, blue. Then this blue line is going there, and then on the blue lines, this blue buffer is driving four red buffers. This blue line goes to this red color. Red buffer is driving three flip-flops. This red is driving these three. This red is driving these three. This red is driving these three. This red buffer is driving these three. And the design of these buffers will be different. Green, red, and blue, that will be different. Green buffer will be the strongest because it is driving so many things, and red buffer is driving only three flip-flops. So now you can see that each of these flip-flop, they will get the clock at the same time. But now the issue is some buffers are added in the circuit. So in when we had placed the cells, we have not taken into consideration the placement of the buffer. Now some extra space has to be required. We have to put the buffers. So the placement, by adding the buffer, there will be some congestion, routing congestion may increase in the placement. Then non-clock cells may have been moved to less ideal locations in that case. So there may be some timing violations because of addition of these buffers. So the designer has to verify those timing violation. There's a tool, prime time, which will tell about the timing variation at each node. The tool will tell, and the designer has to ensure that there is no violation of setup time, no violation of hold time at all the nodes. That designer has to ensure with the help of the tool. So the goal of this clock synthesis is there should be no skew or minimum skew, minimum delay, insertion delay, and minimum power dissipation. So before C2S is done, this is the checklist. As I tell you, here sequences steps are important. So before clock synthesis is done, you have to do the placement, you have to do the power, routing, and your congestion should be acceptable, timing should be acceptable, there should not be any slack, and critical path should meet the timing. So all these things should be there, and then only you will do the clock synthesis. And in doing the clock synthesis, there can be latency between two clocks because you have put buffer. So from this clock, if you are generating two clocks, clock A and B, and the buffers are different in these two clocks, so there can be a latency of each buffer will take some delay. If the delay is zero point 0.5 nanosecond, so then there will be a latency of zero point 0.5 nanosecond difference between clock A and clock B. So this you have to keep in mind while doing this. If you don't want any latency, so you have to design your C2S, the clock synthesis, in such a manner that latency is same for all the cells. And another is a clock tree, clock skew. You have to ensure that there is no skew. Now you can see in this diagram there are two flip flops, yellow and blue. Between this there is a combinational logic, and this is the clock. So first flip flop is getting the clock after three buffers, but the second flip flop is getting the clock after 2 plus 3 after 5 buffers. So there will be a latency due to these three clock tree buffers. These three buffers are there, though that latency will be added in the second flip flop. So the clock will be delayed by the delay of these three clocks, and it might result in a setup violation. As shown here, there are two flip flops. This is B is the delay of the combinational circuit. This is the delay, and if the delay of A and B together is more than the delay of C, this clock, because this means the clock which is going to the first flip flop, it is delayed, then it will result in a setup violation. And if this clock is delayed, the second flip flop clock is delayed, then it will result in a hold violation. So these clocks are very critical, and at each node, the designer has to confirm that there are no setup violations, no hold violations. So after the clock synthesis guidelines, you have to ensure minimum latency, fewer clock tree buffers. Wherever essential, you have to put clock tree buffers. You have to reduce clock power dissipation, less routing resources you have to use. So total skew should be minimized, no timing violation, add buffers only on the logic path, and total power and area has to be minimized. And some signals which are very important, SI, signal integrity, has to be maintained. You have to shield those signals. Shield can be half shield, as you can see here, signal A, signal B, they are having one VSS line, ground line, it's a half shield. Full shield means signal A is being guarded by two VS grounds. So it's there are two ground lines running with the signal A. So it's a full sheet like a coaxial cable. So all critical signals, sensitive signals are used. So clock tree should be constructed using a double width, double spacing rule. So that the signal integrity has to be maintained. Because if the clock signal is integrity is not there, then definitely it is the clock which will log the data for the flip flop, and if that clock signal is not correct, then all the data which is logged, it will be faulty data, and your circuit will malfunction. So this is how it will look like after clocks. You can see this is showing the lines how the clock is getting routed in a chip. So this is known as a H type H tree clocks HT STS clock tree synthesis. H type, it resembles like the letter H, and there are various buffers placed in this, and this is how the clock. And after that, the routing is done. Each cells, all the interconnects, all the wires between the cells, they are used. All the routings are done. And the goal of the routing is there should not be any congestion. Timing has to be minimized. Now, the tool, the software, how he will know the congestion? So first of all, this is the routing. So these blocks are there. These circles, small circles are shown the pins which will be connected. Okay, these small circles, and they are the pins where signals to be connected, like where I am putting my cursor, this one. So these are the pins. So they will be connected. First of all, global routing, the signals which are go through the chip, long signals, long wire are connected, then short wires are connected. There will be short wire, there will be long wires. So global routing and detailed routing, all these things are done. So after the routing, you will see this is the global routing on the left, all long wires. These are all routing, detailed routing. So the chip will look like this. Once, and in a routing, you have to use the lower metal lines, metal 1, M2, M3, M4, those metals are used. And if there are any crosstalks, two metal lines, two signals are going, and there will be a decoupling cap, there will be a capacitance between these two metal lines, and that can cross couple. And so in deep submicron, where the geometries are very small, this may affect that. So transition on one signal will cause unintended logic transition on the other signal. It generates the noise. And to remove this on critical nets, either you have to increase the spacing, as you can see. If you increase the space, your capacitance will be lower. C is equal to epsilon A by D. D is the distance between these two lines. So capacitances become, if the D is more, the capacitance become less. So the cross coupling effect becomes less. Or you can shield it. You can see you are shielded that line. You have put a buffer and you have shielded. So crosstalk is prevented by these two methods. Congestion, the tool, what it will do, the software, it will split the entire chip area in small rectangles, as shown here. This one rectangle, one unit rectangle, and it will allocate routing resource. Like in one rectangle, there can be only 3 routing signals. There are 3 routing resources in one rectangle. So if there are 4 resources are coming, then it's a congestion. So in this example, the routing requirement is 2. So routing resources are 2 in each square. You see this square here. Here 3 lines are coming. But routing resources are only 2. But the tool has given 3, made 3 connections. So this means here it's a congestion. And here there is no congestion because only 2 signals are going. So this is how the congestion is defined. So in this area, how many lines can pass? If the 2 lines can pass, 3 lines are passing, so that is called a congestion. So your replacement has to take care of this. It has to ensure there is no congestion, and the tool will tell this congestion in terms of color. So you can see here yellowish thing, it is showing that in this area there is a congestion. Here it's more green. less yellow is showing, so it's a good layout. It is not the proper thing. And then IR drop analysis tool will do how much dynamic, static IR drop is there at each thing. That tool will tell you, and that tool will tell in terms of the graph only, in terms of the colored picture. And the effect of IR drop will result in metastability issues. It can result in timing violations, and these are the steps how you can reduce IR drop. You, when you are making a power rings, power stripes, you have to add more stripes, or you have to use low power cells, or adding proper vias. You have to do clock gating. You have to put more ground metal fill, staggering switching activity. So all these designers has to do to make less IR drop. And the tool will, you can see this is without IR. You have not considered the IR drop. So lot of this hotspots are there. This red color is a hotspot. So there more IR drop is happening. But here this IR drop you have taken into account in your layout, and there are no hotspots. So this IR drop analysis has to be done initially in your design cycle, so that you are sure that there are no hotspots available, because this hotspot will later raise the temperature of that area, and it will become a problem, reliability problem. After this dummy fills, where metal is not there, metal lines are not there, you have to put some dummy metals, and that is due to the during manufacturing while etching. So if the dummy fills are not there, those area will be etched more, like there will be over etching here, because in this area etching is a chemical reaction. So here more area is available, so the chemical reaction will be more, because the density is low, metal density is low. So what you can do is you can put a dummy metal here, so that it becomes same. So this is a high density, this is a low density. In these two the etching will be different. So but if you, so in this area you have to put a dummy like this. So wide wire should be converted into parallel lines for maximum density. So this is the dummy fills. We have put the dummy metal on the right. The layout will look like this. So all the tool will fill. The software tool, he knows where to put dummy. He will calculate the area, and where the metal coverage is less, it will automatically put some metal packages, metal structures. It will put some structures of the metal. It will automatically put in that chip. After putting this, the chip is now ready. It will look like this. There are corner fills, this one. These are corner fills. This also the software will fill himself, put himself. And then you have to do the verification, physical verification. Whatever so far you have done is okay or not. So physical verification tool, Caliber is a standard physical verification tool. For Caliber needs the rule files, the database of the layout, and the source file. These files we need, and they will do these four things: DRC, design rule checks, it will do layout versus schematic, antenna fixation, and parasitic extraction, it will do. So these four things the physical verification tool will do. Design rule check, there are certain design rules. There are a metal width, metal spacing, as you can see the diffusion to metal. So there may be more than 400, 500 different such rules, and the layout has to, there should not be any violation of these rules. So the software will check all these layers and see that there is no violation anywhere, and wherever there is a violation it will spot that, and you will have to correct that violation. And then there is the antenna checks will be there where the long metal is connected to the gate during etching while fabrication. This long metal acts as an antenna. It gets charged. It accumulates lot of charge because of antenna effects, and that lot of charge can damage the gate oxide. This silicon dioxide is the gate oxide. It can damage the gate oxide. So you have to one has to ensure that there is a lot of the metal line which is directly connected to the gate. It is not more than a particular area. If it is more than a particular area, you split it as shown here. In metal one, I cannot put a 1000 micron line. So I have taken it to M2, M3, and M4, and I have routed through M4. So the connection is going here, but it's not going at M1 level. It is going at M4 level like this. Because if it goes at M1 level, if directly, then this line, this area is much more in when it's getting the chip is getting fabricated. This whole metal one patch will act as a antenna. It will accumulate lot of charge and it will damage this poly red color. But I have not put it here. So I have put M2, then M3, then M4. And after doing M4, this M2 is not visible at all. Okay, so there will not be any antenna effect on that. Because then the visible metal is this much. Or I can put a diode. A diode is also inserted. It can also discharge that charge. N plus diffusion is there and this diode can discharge that. So these two things are used to fix the antenna violations. Tool will tell where to fix these. Some of these are fixed manually. And antenna rule written in IC compiler commands, TCL, is the language used to set up antenna rules, calculate violations, place antenna diodes at metal jumpers. Layout versus schematic LVS, it checks there are no shorts, there are no opens, there are no component mismatches, no extra component is added, no missing component if there are 5 billion components in the front end. So after layouting also there should be 5 billion components, exact match. That is layout versus schematic should be exact. It should be matching. And then you extract the parasitics of the interconnect and then use that parasitic of the interconnect to calculate the delay for static timing analysis, for simulation, for signal integrity. All these tests again you do it, and these results are parasitics. They are in a format which is known as a SPEF, standard parasitic exchange format. So that data is given, and SPF enables the transfer of design specific resistance and capacitances from physical design to timing analysis and simulation tool. So the software will take this in this particular format and that data and will use for the timing calculations and STA calculations. And you can see here from cell 1 to cell 2, these are the two metal lines. So that is the lumped way. Lumped way means there is only one C. Of this line there is a capacitance on lower line. Also there is a capacitance and there is a coupling capacitance CC between these two. There is a capacitance, coupling capacitance between these two. So that is a lumped. And then this is a distributed. Here the each signal is lumped. Here this signal is distributed in three. 1, 2, 3. So you can see there are three resistance and three capacitors of that signal. So that is a distributed R and C. So resistance and capacitance are distributed. and but coupling capacitance are not taken into account. So here in the last picture, the coupling capacitance is also distributed. So these are the different three models of R and C of the parasitic, and normally the tool selects the middle one, distributed RNC. The tool will select this, and based on that, it will do this. So after this, you have done the post layout verification, everything you have done. You have done the static verification, dynamic verification using test benches. You have done the frequency check, simulation, everything. Your design is ready for static timing analysis. Again, you will do. Prime time is the tool it will do. It will need .v file, .v, .lib, .sdf, and it will need SPEF, SDF, and SDC, and it will generate the timing report. This tool will take all these input. IC compiler and caliber tool jointly will take the output of design compiler is netlist, SDC, MV, and lib. Then the output goes to IC compiler and caliber along with .v, .spf files. It goes to prime time tool for timing analysis, and it will give the timing report. And if the timing report is okay as per your requirement, the chip is okay, and you can release the chip. And then finally the sign off is done. Then you generate the automatic test pattern generators. You generate the test patterns, which are the truth table, which will be used for working of that chip. And finally the circuit is, and the tool which is used for generating the test pattern is at Tetramax synopsis tool. Tetramax is used. It will generate the test patterns, and you can use it. So this way the complete you can say the layout is used. So there are various tools used in this layout, and all these tools, all these software, they are basically because of the number of you can say modules. The cells are quite high in millions and billions, and if there is some machine learning used nowadays, a lot of people, these main two companies, Synopsys and Cadence, for tools which are used in below 10 nanometer. So they are using EAML in a big manner to make this tool efficient and do the work in a lower time. So with this, I will stop if you have, and I will take your questions. If you have any question, please feel free to ask.
So, participants, if you are having any queries, please raise it or put it in the chat box.
Corner analysis, multi-corner simulation. Basically, they are the simulations which are carried at various corners. Various corners means like you simulate the circuit at room temperature, high temperature, low temperature, because VT will change. You simulate the circuit at low VT, high VT. VDD power supply is say 1.8 volt, but it will not be exactly 1.8. It can be low 1.6 volt, then high. So low VDD, high VTD, you simulate at different corners. So that is a Monte Carlo corner. So at different corners, you try to simulate the circuit and see the circuit is working, because there will be drift. You are designing a chip at 25 degree, but if the chip goes in a car engine, so their temperature will be 125. There also it has to work. And in a winter, the temperature may be less. There also it has to work. So you have to simulate the conditions accordingly at different corners. P is your power, voltage, temperature. And P is process. Process in terms of your threshold voltage. Like the transistor can be fast or slow. That is the process. Voltage, VDD min, VDD max, temperature, T min, T max. So various combinations, there will be around 45 combinations, 45 corners will become.
Any other questions?
So if there are any other questions, kindly conclude the session, Simi.
Okay. So I think no more questions are left. So we can conclude the session. So, Jatna sir, we extend our sincere gratitude for your valuable presence and for delivering such a insightful and enriching session. Once again, thank you so much, sir.
Thank you. Thank you, madam. Thank you. Thank you very much. Thank you.
Okay, okay, thank you, sir. So, dear participants, please note that there will be two separate links for today's session. So, participants are required to fill the both links for attendance. The attendance will be considered only upon Google Meet presence and completion of both forms. So, everyone make please sure to complete the both forms. Okay, and also one more thing that tomorrow's session will be begin at 6 p.m. So, once again, thank you all. Thank you all for your participation. Let's see tomorrow again. Thank you.